time is going to be evolving as we run our model, just as time evolves in nature. So we need to use these equations to solve for future voltages and currents. And if we solve for the most future value in each equation, we can get what are called update equations. So first, which term is the most future value in these equations? Well, let's look at the first equation right now. And if we look at the moments in time, we have n plus a half, n plus a half, n plus 1, n plus 1, and n. So if we compare all these, n plus 1 is the most future voltage value that we have in this equation. All the other voltages are earlier in time. This is n is one whole time step earlier in time. This is also, these are past voltages that would already be stored in our computer or solved for earlier in time. And then what about for the second equation? The second equation, we have n plus a half, n minus a half. So these two are the most future values. So in other words, if we solve for this, move the terms around in these equations so that we solve for the most future value, say we have k plus a half, n plus 1 half, and we move all the other terms to the right side, and same thing here, we have n plus 1, the most future voltage, and everything else on the right side, then we can come up with what are called the update equations. I'm not going to go through all the details of rearranging these terms. It's straightforward, maybe a little tedious, but straightforward. So this is the second telegrapher's equation that I'm looking at here. So we're solving for the most future value. We're going to get something of the form where we have C1, a coefficient, times two neighboring voltages at time step n. And then we can have another coefficient times the current at one time step earlier. So this is the form of the update equation that we would get. And C1 is equal to minus delta t, 2 delta t, over delta t delta z r prime. This is just from rearranging all these terms. And the second coefficient is 2 L prime minus delta t r prime. So if I were to describe this equation in words, I would say the future current that we want to solve for is equal to this coefficient based on the transmission line parameters and our FDTD grid parameters, delta t and delta z, times the difference between the two neighboring voltages. They're a half a time step earlier and one to the left and one to the right, plus another coefficient times the current at the same location in space, but one time step earlier than the one we're solving for. And going through the same process for the first telegrapher's equation, we get something also of the form. We have the future voltage is equal to a coefficient times the difference of the two neighboring currents, one to the left and one to the right, both 1/2 of a time step earlier than the voltage we're solving for. And another coefficient times the voltage, same location and one time step earlier than the one we're solving for. And here, C3 coefficient is 2 delta t, and we have delta t, delta z. I will provide these later when you're actually programming it. C4 to C prime. All right, so we have these. This is a G prime. So all in all, this is what we wind up with. At the beginning of our simulation, we can define these 4 coefficients, and then we would iterate through time and solve these 2 update equations every single time step. Every half time step, we update a new component. The first equation we'll say at half time steps, and the second equation at integer time steps. So as a last step here, before we end, and next time you'll be implementing this kind of a code, before we finish today, just spend a minute and write a high-level outline. An outline of the code that you would build to solve these 2 equations. And you'll probably need to create some sort of a loop. We'll be working with MATLAB for this, so don't worry too much about syntax or anything, but just write a very high-level outline of a loop you would create to solve these equations in time.